Chapter 2 review. Now I gotta warn you, Chapter 2 review is not enough. I couldn't find enough problems in it for what we need, but I'm gonna do it anyways. You still have, if you notice in it, there's no limit by picking numbers like we have on the homework, but it refreshes certain ideas. Chapter review starts with true or false. I don't give true or false on a test, but I'm going to use those to kind of elaborate a bit because they're very limited. This book has very limited chapter review problems. So, in the following exercise, justify your answer with a proof or a counterexample. It says a function has to be continuous at x equal a if the limit exists. A function has to be continuous at x equal a if the limit exists. Okay. So if I think of the following graph, if I take the limit and call this a, if I take the limits from the left and the limits from the right, isn't that a 1? The limit exists. A function has to be continuous at a if the limit exists. This function is not continuous at a, but the limit still exists. So that's false. $2.10. It says, again, graphing is the best way you could kind of visualize it. It says, if there is a vertical asymptote at x equal a, so how do you get a vertical asymptote? Wouldn't that mean that you're looking at, like, of course, there's some function there, and you could have multiple factors, but one of them has to be x minus a, true? That's how we get a vertical asymptote. So if there is a vertical asymptote x equal a for a function, then f is undefined. Well, that's true. How do you find vertical asymptotes? Don't you say, well, what's the domain? X cannot be a in this case because it's undefined there. And yes, that will be a vertical asymptote. That's true. Now, from this point on, we're going to do things algebraically. We're not going to use a calculator, which means calculator work is not accepted. And if you recall limits, I know it's been a while, to find the limit, unless you're seeing an absolute value, basically you plug the value in. If you get a number, you're done. If you get a number over 0, it doesn't exist. And if you get 0 over 0, you would manipulate the problem. If I start with the first example, that's a polynomial. I'll plug 3 in. I'll get a 4. Oh, okay, that's the limit. You're done. That's basically it. When I look at the second example, okay, I plug the pi over 2 in. I'll get cotan of pi over 2 is 0, cosine is 0. I need to manipulate that. Well, how do you manipulate that? We say, all right, 1 over cosine of x, and we do know that cotan of x is cosine of x over sine of x. Now, we know that cosines cancel out. That would be the limit as x. That would be, when you plug the value in, that would simply be 1 divided by the sine of pi over 2. And the sine of pi over 2 is 1, so that makes that limit a 1. Rational functions, again, you plug the value in. If you happen to get 12 minus 4 minus 8 is 0, and 4 minus 4 is 0. So in that case, what do? Well, you factor. The denominator will be the difference of squares, and the top will be 3x and an x, a minus 2 and a plus 4. That will be 3x squared minus 6 plus 4. Yep, and those cancel out. And once you cancel a factor, you reset that shortcut. You plug the value in again and you see what you get. And in this case, if I substitute x with a 2, I will get a 6 plus 2, that's a 10. 2 plus 2 is 4, and that's 5 halves. The next problem, I see a rational and I see a radical. I plug one in. 1 minus 1 is a 0. And 1 minus 1 is a 0, so I'm getting 0 over 0. If I see a radical, I know what to do. I multiply by the conjugate. Hopefully we have that down. Limit as x approaches 1. The top, the x squared minus 1 factors into x minus 1, x plus 1, times the square root of x plus 1. The denominator, since those are conjugates, you get the first squared, which is x, minus the second squared, which is 1. Those cancel out. You're looking at the limit as x approaches 1 of x plus 1 times the square root of x plus 1. Substitute x equal 1, you get 1 plus 1 into 1 plus 1. 2 times 2 is a 4. And how about this problem? Let me move this problem right there. You know what? Let's leave it there. So here, if I substitute a 4 in, I'll get 1 over 2 minus 2. I'll get 1 over 0. That means this limit either positive or negative infinity, but we don't care much about that. We just say it doesn't exist and everybody's happy. How about here? It says use the squeeze theorem. Well, the key to use the squeeze theorem, if you put 0 in, you get 0 cubed times the sine of pi over 0. We have a problem. This is undefined. Yet 0 times any number is 0, but a number that's defined. So what do? We say, well, look, x cubed, the sine of pi over x is less than or equal and bigger than or equal. Well, what is the smallest value a sine could ever be? Is a negative 1. And what's the largest value a sine could ever be? That's a 1. So we know that x cubed, the sine of pi divided by x, is between x cubed and negative x cubed. Now, if I take the limit as x approaches 0 of each of those, I'll be looking at the limit as x approaches 0 of negative x cubed, the limit as x approaches 0 of x cubed, the sine of x cubed, of x cubed, the sine of pi over x, and I'll be taking the limit as x approaches 0 of positive x cubed. Can I shrink that a bit? And what do we know? We know that if you plug 0 in, that's 0. And if we plug 0 in, we get 0. Well, algebraically, what's a quantity? What's the number that is bigger than or equal to 0 and less than or equal to 0? There's only one number that works, 0. And that's how we set the squeeze theorem. And of course, if you took this in high school, squeeze theorem is called the Sandwich theorem, but it's still ST, so that still works. Determine the value of c such that the function remains continuous. Okay, well, let's see. What does continuous mean? Continuous means that the limit as x approaches c of f of x equals f of c. Well, first things first, does f of c exist? Do you see the equals in the bottom? So if you plug C in, you get 2 times C. It does exist. Secondly, does the limit as x approaches C of f of x exist? Well, let's see. If I take the limit as x approaches C from the left, that means x is less than C. You're dealing with this, and since that's a polynomial, I plug that in and I'll get 2C. If I take the limit as x approaches C from the right, that means C is bigger, x is bigger than C. Let me make sure. C to the right. Yeah, x is bigger than C. Then I'm using x squared plus 1. And if I plug C in, because that's a polynomial, that's C squared plus 1. Now, f of C exists. For the limit to exist, I need 2C to equal C squared plus 1. If those are equal, then the limit will exist. Well, that means I'm looking at C squared minus 2C plus 1 equal to 0. Or C minus 1 squared equal to 0. That means C minus 1 equals 0. Or C equal 1. If C equal 1, f of 1 will be a 2. That checks. And if I put a 1 right there, that will be a 2. And if I put a 1 right there for C, that will be a 2. And this limit will be a 2. Therefore, this will be a 2 and the limit will be a 2. And therefore, the function will be continuous at C. And again, this is not enough. They didn't really put everything in there, but it's a good reminder of what to do.